Abstract algebra groups. First of all, we will discuss binary operation. Definition of binary operation. Let V have any set S. We form a new set S cross S by Cartesian product, and the elements of this new set S cross S are ordered pairs AB, where A and B both are elements of S, and AB and BA in generally are not same. They are distinct elements and they are equal if and only if A is equal to B. A binary operation denoted by star on S is a function from S cross S into S, and the ordered pair S star is known as binary structure, and we also can say it an algebraic structure. We take AB, an element from S cross S, and S star is a function from S cross S to S, so A star B is an element of S. This means when we take two elements A and B from S and we form a new element A star B, this new element is also in S. This is how the binary operation works. For example, addition, subtraction, and multiplication are binary operations for the set of integers, as when we add, subtract, or multiply any two integers, the result will also be an integer. But the division is not a binary operation for the set of integers, as when we divide two integers, the result need not be an integer again. Definition of group. Let G be any non-empty set together with a binary operation star. Then G is said to be group under operation star, or the algebraic structure G star is said to be group if the following conditions are satisfied. Condition first is associativity. Here, if A star B star C is equal to A star B star C for all A, B and C from G. Condition second, identity. If there exists an element denoted by E in G such that A star E is A and E star A is also A for all A belonging to G. Condition third, inverse. If for each element A from G there exists an element B in G such that A star B or B star A is the identity element. A group is said to be a commutative group or Abelian group if the following property is satisfied. A star B equals B star A for all A and B in G. Any group is non-Abelian or non-commutative group if there exists at least one pair of elements A and B such that A cross B not equal B cross A. So group is a set together with an associative operation star such that there is an identity and every element has an inverse, and any pair of element can be combined to create any element, but this element is within the given set. This later condition is called as the closure property, and one should verify the closure property when testing for any algebraic structure to be a group. Let's discuss some examples. Example first. Show that Z plus is an Abelian group. Here Z is the set of integers and plus is the ordinary addition. First of all, we will discuss the closure property. Here we need to show that if we take any two elements A and B from Z, then we add them A plus B, and that also should be in Z. So whenever we take any two integers a and b and we add them, then a plus b is again an integer, so the closure property holds. Associative property, a plus b plus c will be definitely equal to a plus b plus c, so associative property also holds. Identity, 0 is in Z and 0 will work as identity. As per the definition of identity, whenever identity is operated on an element, there should be no difference. Means a plus identity must be a again, and this is only possible in set of integers when we take identity as 0. So 0 plus a is equal to a, and a plus 0 is also is equal to a. So a plus 0 and 0 plus a both are is equal to a for all a from Z. Inverse, for each a we can find minus a in set of integers such that a plus minus a will be identity and minus a plus a will also be identity, and identity here is 0 in case of set of integers. Commutativity, whenever we take two integers a and b from set of integers, then a plus b will be equal to b plus a. So all 5 conditions are satisfied for an algebraic structure to be an abelian group. Similarly, it can be shown that R plus and Q plus are also commutative groups or abelian groups. Next example, let's take set of integers and the usual multiplication, then algebraic structure Z cross is not a group, as we can find some integer which doesn't have inverse in Z. Number 1, closure property is satisfied, as multiplication of any two integers will be an integer again. Associativity also holds trivially, there is no need to prove. 1 is the identity element in set of integers, because if we take any element a from Z, then 1 into a will be again a. We cannot find an element a belonging to Z such that 2a is equal to 1. So 2 belonging to Z does not have any inverse in Z. Means we have 2 from set of integers and we cannot find any element a in Z such that 2a is 1. Next example, let we have a set containing element 1, minus 1, iota and minus iota. We need to prove that this set is a group under complex multiplication, as this set has finite number of elements, and in this type of cases we will be using the composition table known as group table or Cayley table. We select first element in the column and multiply with all the elements of this row one by one and obtain this first row. Then we take the second element from the column and multiply each element of this row one by one and obtain the second row, and so on, and we get this table. Now all the elements of the table are elements of S, so the closure property holds. Associativity holds trivially for the multiplication of complex numbers. Clearly 1 is the identity. The way to find the identity is when an element multiplied by an element gives that element, then that element is identity. Here 1 multiplied by 1 gives 1, so 1 is the identity. Now we find inverses. To find inverse of this element, we find identity below this, and identity is this, and then we find element in front of identity, which is 1. So inverse of 1 is 1. Now we find inverse of minus 1. We find identity below this element, which is 1, and then we find element in front of this identity, which is minus 1. So inverse of minus 1 is minus 1. Similarly, the inverse of eta is minus eta, and the inverse of minus eta is eta. So the inverse of each and every element holds within the given set. Fifth property, the matrix out of this Cayley table is a symmetric matrix. This means the commutativity holds, means A cross B will be equal to B cross A. So the algebraic structure S cross is an abelian group or a commutative group. Set of all 2 cross 2 matrices with real entries is a group under matrix addition defined as this. Closure property and associativity hold trivially as R plus is a group. This matrix will act as an identity element, and if this is any random matrix from the set, then this matrix will act as an inverse of this matrix. Again, A plus B is equal to B plus A for all A and B in set of reals, so commutativity also holds. So the set of all 2 cross 2 matrices of this kind with real entries is an abelian group or a commutative group. Set G of all 2 cross 2 non-singular matrices with real entries is a non-abelian group under matrix multiplication denoted by cross, defined as this. Closure property and associativity hold trivially as set of reals is a group under casual multiplication. This element will act as an identity, and we can find inverse of each element, as inverse in matrices is defined as adjoint of A divided by determinant of A, and as we have a collection of all non-singular 2 cross 2 matrices, so this will never be 0, so inverse is well defined. Now for any two elements A and B from Z, we cannot say that AB is equal to BA for each element. That is, if we find at least two elements A and B such that AB not equal to BA, then we will say that the group is not an abelian group, and we can take two elements, first element A and second element B. Now we perform AB, and AB is this matrix, and then we find B into A, and that is this matrix, and the right hand side of both these calculations are not same, so G cross is not an abelian group. Z minus the set of integers under usual subtraction is not a group, as associativity doesn't hold. If we take three elements 2, 3 and 4, and we find 2 minus 3 minus 4 and 2 minus 3 minus 4, then both these results are not same, so associativity doesn't hold. So set of integers under usual subtraction is not a group. Let G be set of all 2 cross 2 non-singular matrices with entries from the set of integers. The elements A, B, C and D are all integers. Then this G is not a group under matrix multiplication denoted by cross, and matrix multiplication is defined as this. Here we have element 2001 and this element is belonging to the set G, but we cannot find any element in G which is inverse of this element. So we cannot say that inverse of each element of G exists. So the set G under matrix multiplication is not a group. We have set of reals R and we define an operation star as A star B is A plus B plus 2 for all A and B from set of reals. Then we need to prove that the algebraic structure R star is a group. First of all, we will discuss the closure property. Closure property holds as for any two real numbers A and B, A plus B plus 2, that is A star B, is also a real number. Associativity, A star B star C comes out to be A plus B plus C plus 4, and A star B star C also comes out to be A plus B plus C plus 4. So associativity also holds. Now we find the identity element. -2 will work as identity element for all A belonging to R. Let's find how. A star -2 will be A plus -2 plus 2, and this -2 and 2 will be cancelled out and we will get A. So A star -2 will be A, and similarly -2 star A will also be A. So identity also exists. Now we will prove that inverse for every element of R exists. For any element A of R, -4 minus A will act as an inverse. Let's see how. A star -4 minus A will be A plus -4 minus A plus 2, and that will come out to be -2. Similarly, -4 minus A star A will come out to be -2. So inverse for each element of R also exists. Now we show that the commutativity also holds. A star B is A plus B plus 2 and B star A is B plus A plus 2, and A plus B and B plus A are same, so we can write this as A plus B plus 2, that is A star B. So B star A is equal to A star B for all A and B belonging to R. So the commutativity also holds. So the algebraic structure R star, where star is defined as this, is an abelian or commutative. Let we have a set G and that contains element of form 8A plus 14B, where A and B are integers. We need to prove that G is a group under integer addition. Closure property. If we take any two elements from the set G and we perform addition on them, then we get again an element which is from G. So the closure property holds. Associativity. We take three elements A, B and C from G. We perform A plus B plus C, which is this, and then we perform A plus B plus C, which is this, and this is equal to A plus B plus C. So associativity holds. Now we try to find identity. 0 will act as an identity, as 0 can be written as 8 into 0 plus 14 into 0. So 0 belongs to Z, Now we prove that 0 is identity. Means when we add 0 in any element of G, then we get that same element. 8a plus 14b is an element of G, and we add 0 into this. That is 8 into 0 plus 14 into 0, and we again get 8a plus 14b. So identity element also exists. Now we try to find inverse. Let 8a plus 14b is any random element from G. Then 8 into minus a, that is minus 8a, plus 14 into minus b, that is minus 14b. So minus 8a minus 14b also exists in G. And we claim that for any element 8a plus 14b, minus 8a minus 14b acts as an inverse. So if we add 8a plus 14b and minus 8a minus 14b, we must get an identity, and identity as we have obtained earlier is 0. So performing this addition we get 0, and minus 8a minus 14b plus 8a plus 14b is also 0. So inverse also exists. Prove that any set O, the set of odd integers, is not a group under addition. Here we will show that the closure property doesn't hold. 1 and 3 both are in the set O, but 1 plus 3 is 4, and 4 is not in the set O, as 4 is an even integer. So O under addition is not a group. Set of all 2 cross 2 matrices with real entries under matrix multiplication is not a group. Here we will prove this by showing that the inverse of each element may not exist. Let V have this element, any random element from the given set, then its inverse will be this element, and the existence of inverse depends on the quantity AD minus BC. If AD minus BC is 0, then inverse of this element will not exist. So we cannot say that set of all the 2 cross 2 matrices with real entries under multiplication is a group. Prove that R square containing all the ordered pair AB, where A and B are from capital R, set of reals, is a group under component-wise addition, defined as A1 B1 plus A2 B2 is A1 plus A2 B1 plus B2. First of all, we will discuss the closure property. Let A1 B1 and A2 B2 be any two elements from R square, then we add them up. A1 B1 plus A2 B2 will be A1 plus A2 B1 plus B2, and A1 plus A2 is also in R and B1 plus B2 is also in R. So this is an element. So this is an element in R square. So the closure property holds. Now associativity, as shown here, when we first associativity, A1 B1 plus A2 B2 plus A3 B3 will be A1 plus A2 plus A3 B1 plus B2 plus B3, and again when we add A1 B1 in A2 B2 plus A3 B3, we again get A1 plus A2 plus A3 B1 plus B2 plus B3. So associativity also holds. Identity element, clearly 0 0 belongs to R square, and this is the identity element of the set. Inverse, for any element AB in R square, minus A minus B is in R square, and this will act as an inverse of the element AB. Commutativity, Commutativity also holds as shown here. So R square plus is an abelian group or a commutative. Zn, the group of integers under addition modulo. Here there is a constraint on n. N is an integer greater than or equal to 1. Then corresponding Zn will be having elements 0, 1, 2, 3 up to n minus 1. Zn is formed by dividing all the integers one by n and collecting the remainders. So we get a set of elements 0, 1, 2, 3 up to n minus 1. Now we will prove that this set Zn is a group under addition modulo. Now we define the addition modulo. If we have two elements a and b, then a plus mb is r, and r is obtained by dividing a plus b by m. Here r is the least non-negative remainder when a plus b, that is the ordinary sum of a and b, is divided by m. And this addition modulo can be written as a plus b mod m. Now we discuss some properties of addition modulo m. A plus b mod m can be written as mod m of a mod m plus b mod m. And if we have a mod m is equal to b mod m and c mod m is equal to d mod m, means when we divide a by m and we get a remainder, and the same remainder is obtained when we divide b by m, and when we divide c by m we get a remainder, and the same remainder is obtained when we divide d by m. Then we can say that when a plus c is divided by m and a remainder is obtained, then the same remainder is obtained when we divide b plus d by m. Again, a mod m is equal to b mod m implies a plus k mod m is equal to b plus k mod m for every integer. A mod m also can be written as a mod m mod m. It means when we find a mod m, means we have divided a by m and obtained remainder. The remainder can be 0, 1, 2, 3, 4 up to m minus 1. And we again apply mod m, that is we divide that remainder by m, then there will be no effect on that remainder. When a and b are two integers such that a minus b is divisible by a fixed positive integer m, then we have a is congruent to b mod m. Thus a is congruent to b mod m if and only if a minus b is divisible by m. For example, 13 is congruent to 3 mod m, as 13 minus 3 will be 10 and 10 is divisible by 5. Let's see some examples. Question is, find a group with 5 elements. We find Z5. The elements of Z5 are 0, 1, 2, 3, 4. And this is a set with 5 elements, and we will prove that this is a group under the addition modulo 5, as this set is a finite set, means this has a finite number of elements. So we will be proving that this set under this addition modulo is a group by using the Cayley table or the composition table. As discussed earlier, we can form the composition table. Here we take the first row and the first element of this column and we add this element one by one in each element of this row and divide the results by 5, and we obtain this. Then we take the second element of the column 1 and we add this into each element of this row, and then we divide that result by 5 and we write the remainder here. When we add 1 into 3, we get 4, and when we divide 4 by 5, we get remainder 4. When we add 1 into 4, we get 5, and then we divide 5 by 5, we get remainder 0. By doing this, we get this whole table. Now, we discuss the properties or conditions for a set to be a group. First of all, we discuss the closure property. As it is obvious that all the elements obtained in the Cayley table belongs to Z5. So, the closure property holds. Associativity can be proved by using the properties of addition modulo discussed above. Identity. It is evident that 0 is the identity element. Inverse. Using the Cayley table, it can be shown that each element has its inverse. For example, if we try to find the inverse of 2, we must locate identity below 2, and identity is here, and 3 is in front of identity, so 2 is the inverse of 3 and 3 is the inverse of 2. So inverse also exists for each element of Z5 under addition modulo 5. Now we discuss commutativity. The matrix T obtained from the table is a symmetric matrix. That means A star B will be B star A. So the commutativity also holds. So Z5 under addition modulo 5 is a commutative group. Similarly, we can find any group of order 6 as Z6 under addition modulo 6, and we can find group of order 10 Z10 under addition modulo 10, and so on. Next example, prove that Zn is a group under addition modulo n, or prove that the algebraic structure Zn plus n is a group. Closure property. As for any a and b belonging to Zn, a plus modulo nb will be also belonging to Zn. Associativity. For any 3 elements a, b, c from Zn, we can easily show that a plus b plus c will be equal to a plus b plus c. Identity 0 is evidently the identity element of Zn. Inverse. For any element a from Zn, we can find another element b from Zn such that a plus b is equal to n. Now, a plus modulo n b will be a plus b mod n, and a plus b is n, so n mod n. N mod n means divide n by n and obtain the remainder, which is 0, and 0 is the identity element of Zn, so a plus modulo n b is identity, and similarly b plus modulo n a is identity. So b is the inverse of a and a is inverse of b. So the inverse also exists. Commutativity. For any a and b belonging to Zn, a plus modulo n b will be a plus b mod n, and as a and b are integers, so a plus b will be equal to b plus a, so b plus a mod n, and this can be written as b plus modulo n a. So a plus modulo NB will be equal to B plus modulo NA. That is, the commutativity also holds. So this algebraic structure is commutative group. Some assignments. Question first. Prove that Q plus, which is a set of positive rationals, is a group under usual multiplication. Question second. Give two reasons why the set of odd integers is not a group under addition. Question 3. If A and B belonging to Z and Z is an abelian group, then prove that AB square is A square into B square. Question 4th. Prove that for all A of any group, inverse of A inverse is again A. Question 5th. Let G be a set containing 2 cross 2 matrices of this kind where A is any real number and A is not equal to 0, then show that G is a group under matrix multiplication. Question 6th. Suppose that the table given below is a group table. You are supposed to fill in the blanks, considering that each element of the group appears exactly once in each row and each column.